Earth's atmosphere consists mostly of nitrogen and oxygen. More solar energy is received by tropical regions than polar regions, and is redistributed by atmospheric and ocean circulation. Greenhouse gases also play an important role in regulating the surface temperature. A region's climate is not only determined by latitude, but also by elevation, and by proximity to moderating oceans. Among other factors, severe weather, such as tropical cyclones, thunderstorms, and heat waves, occurs in most areas and has a large impact on life. Earth's gravity interacts with other objects in space, especially the Moon, which is Earth's only natural satellite. Earth orbits around the Sun in about 365.25 days. Earth's axis of rotation is tilted with respect to its orbital plane, producing seasons on Earth. The gravitational interaction between Earth and the Moon causes tides, stabilizes Earth's orientation on its axis, and gradually slows its rotation. Earth is the densest planet in the Solar System and the largest and most massive of the 4 rocky planets. The modern English word earth developed, via Middle English, from an Old English noun most often spelled eor. 25, it has cognates in every Germanic language. And their ancestral root has been reconstructed as *ero. In its earliest attestation, the word eor was already being used to translate the many senses of Latin terra and Greek gay, the ground. Its soil, dry land, the human world, the surface of the world, including the sea, and the globe itself. As with Roman terra, new continental crust forms as a result of plate tectonics, a process ultimately driven by the continuous loss of heat from Earth's interior. Over the period of hundreds of millions of years, tectonic forces have caused areas of continental crust to group together to form supercontinents that have subsequently broken apart. At approximately 750 Ma, one of the earliest known supercontinents, Rodinia, began to break apart. The continents later recombined to form Pannotia at 600 to 540 Ma, then finally Pangaea, which also began to break apart at 180 Ma. 55. The most recent pattern of ice ages began about 40 Ma. 56, and then intensified during the Pleistocene about 3 Ma. 57. High and middle latitude regions have since undergone repeated cycles of glaciation and thaw, repeating about every 21,000, 41,000 and 100,000 years. 58. The last glacial period, colloquially called the last ice age, covered large parts of the continents, up to the middle latitudes, in ice and ended about 11,700 years ago. 59. Origin of life. Chemical reactions led to the first self-replicating molecules about 4 billion years ago. A half billion years later, the last common ancestor of all current life arose. 60. The evolution of photosynthesis allowed the sun's energy to be harvested directly by life forms. The resultant molecular oxygen, O2, accumulated in the atmosphere and due to interaction with ultraviolet solar radiation, formed a protective ozone layer, O3, in the upper atmosphere. 61. The incorporation of smaller cells within larger ones resulted in the development of complex cells called eukaryotes. 62. True. Multicellular organisms formed as cells within colonies became increasingly specialized, aided by the absorption of harmful ultraviolet radiation by the ozone layer. Life colonized Earth's surface. 63. Among the earliest fossil evidence for life is microbial mat fossils found in 3.48 billion-year-old sandstone in Western Australia. 64. Biogenic graphite found in 3.7 billion-year-old metasedimentary rocks in western Greenland. 65. And remains of biotic material found in 4.1 billion-year-old rocks in Western Australia. 66. 67. The earliest direct evidence of life on Earth is contained in 3.45 billion-year-old Australian rocks showing fossils of microorganisms. During the Neoproterozoic, 1000 to 541 Ma, much of Earth might have been covered in ice. This hypothesis has been termed snowball Earth, and it is of particular interest because it preceded the Cambrian explosion, when multicellular life forms significantly increased in complexity. 71. Following the Cambrian explosion, 535 Ma. There have been at least 5 major mass extinctions and many minor ones. 72. 73. Apart from the proposed current Holocene extinction event, the most recent was 66 Ma. When an asteroid impact triggered the extinction of the non-avian dinosaurs and other large reptiles, but largely spared small animals such as insects, mammals, lizards and birds. Mammalian life has diversified over the past 66 Mas. And several million years ago an African ape gained the ability to stand upright. 74. This facilitated tool use and encouraged communication that provided the nutrition and stimulation needed for a larger brain, which led to the evolution of humans. The development of agriculture, and then civilization, led to humans having an influence on Earth and the nature and quantity of other life forms that continues to this day. Main article. Figure of the Earth. Further information. Earth radius and Earth's circumference. See also. List of highest mountains on Earth. Chimborazo, whose summit is the point on Earth's surface that is farthest from Earth's center. 84. The shape of Earth is nearly spherical. There is a small flattening at the poles and bulging around the equator due to Earth's rotation. 85. Therefore, a better approximation of Earth's shape is an oblate spheroid, whose equatorial diameter is 43 kilometers, 27 miles, larger than the pole-to-pole diameter. 86. The point on the surface farthest from Earth's center of mass is the summit of the equatorial Chimborazo volcano in Ecuador, 6,384.4 kilometers or 3,967.1 miles. 87, 88, 89. The average diameter of the reference spheroid is 12,742 kilometers, 7,918 miles. Local topography deviates from this. Main article. Structure of the Earth. Geologic layers of Earth. 98. Earth cut away from core to exosphere. Not to scale. Depth. 99 kilometer. Component layer density G. Here is the asthenosphere, a relatively low viscosity layer on which the lithosphere rides. Important changes in crystal structure within the mantle occur at 410 and 660 kilometers, 250 and 410 miles below the surface, spanning a transition zone that separates the upper and lower mantle. Beneath the mantle, an extremely low viscosity liquid outer core lies above a solid inner core. 102. Earth's inner core may be rotating at a slightly higher angular velocity than the remainder of the planet, advancing by 0.1 to 0.5 degrees per year, although both somewhat higher and much lower rates have also been proposed. 103. The radius of the inner core is about 1/5 of that of Earth. Density increases with depth. as described in the table on the right. The major heat-producing isotopes within Earth are potassium-40, uranium-238, and thorium-232, 104, at the center. The temperature may be up to 6,000 degrees Celsius, 10,830 degrees Fahrenheit, 105, and the pressure could reach 360 gigapascals, 52 million psi, 106, because much of the heat is provided by radioactive decay. Scientists postulate that early in Earth's history, before isotopes with short half-lives were depleted, Earth's heat production was much higher. At approximately 3 GeA, twice the present-day heat would have been produced, increasing the rates of mantle convection and plate tectonics, and allowing the production of uncommon igneous rocks such as komatites that are rarely formed today. 107, 108. The mean heat loss from Earth is 87 milliwatts m-2, for a global heat loss of 4.42 times 1013 W, 109. A portion of the core's thermal energy is transported toward the crust by mantle plumes, a form of convection consisting of upwellings of higher temperature rock. These plumes can produce hot spots and flood basalts. 110. More of the heat in Earth is lost through plate tectonics, by mantle upwelling associated with mid-ocean ridges. The final major mode of heat loss is through conduction through the lithosphere, the majority of which occurs under the oceans because the crust there is much thinner than that of the continents. 111. Tectonic plate. Earth's mechanically rigid outer layer, the lithosphere, is divided into tectonic plates. These plates are rigid segments that move relative to each other at one of 3 boundaries types. At convergent boundaries, 2 plates come together. At divergent boundaries, 2 plates are pulled apart, and at transform boundaries, 2 plates slide past one another laterally. Along these plate boundaries, earthquakes, volcanic activity, mountain building, and oceanic trench formation can occur. 113. The tectonic plates ride on top of the asthenosphere, the solid but less viscous part of the upper mantle that can flow and move along with the plates. As the tectonic plates migrate, oceanic crust is subducted under the leading edges of the plates at convergent boundaries. At the same time, the upwelling of mantle material at divergent boundaries creates mid-ocean ridges. The combination of these processes recycles the oceanic crust back into the mantle. Due to this recycling, most of the ocean floor is less than 100 ma old. The oldest oceanic crust is located in the western Pacific and is estimated to be 200 ma old, 115, 116, by comparison. The oldest dated continental crust is 4030 ma, 117, although zircons have been found preserved as clasts within Eoarchean sedimentary rocks that give ages up to 4400 ma, indicating that at least some continental crust existed at that time. 7 major plates are the Pacific, North American, Eurasian, African, Antarctic, Indo-Australian, and South American. Other notable plates include the Arabian Plate, the Caribbean Plate, the Nazca Plate off the west coast of South America, and the Scotia Plate in the southern Atlantic Ocean. The Australian Plate fused with the Indian Plate between 50 and 55 ma. The fastest moving plates are the oceanic plates, with the Cocos Plate advancing at a rate of 75 mm. Main article: Gravity of Earth. Earth's gravity measured by NASA's GRACE mission, showing deviations from the theoretical gravity. Red shows where gravity is stronger than the smooth, standard value, and blue shows where it is weaker. The gravity of Earth is the acceleration that is imparted to objects due to the distribution of mass within Earth. Near Earth's surface, gravitational acceleration is approximately 9.8 meters. The main part of Earth's magnetic field is generated in the core, the site of a dynamo process that converts the kinetic energy of thermally and compositionally driven convection into electrical and magnetic field energy. The field extends outwards from the core, through the mantle, and up to Earth's surface, where it is, approximately, a dipole. The extent of Earth's magnetic field in space defines the magnetosphere. Ions and electrons of the solar wind are deflected by the magnetosphere. Solar wind pressure compresses the day side of the magnetosphere, to about 10 Earth radii, and extends the night side magnetosphere into a long tail, 135, because the velocity of the solar wind is greater than the speed at which waves propagate through the solar wind. A supersonic bow shock precedes the dayside magnetosphere within the solar wind. 136 charged particles are contained within the magnetosphere. The plasmasphere is defined by low-energy particles that essentially follow magnetic field lines as Earth rotates. 137, 138. The ring current is defined by medium-energy particles that drift relative to the geomagnetic field, but with paths that are still dominated by the magnetic field. 139, and the Van Allen radiation belts are formed by high-energy particles whose motion is essentially random, but contained in the magnetosphere. 140, 141. During magnetic storms and substorms, charged particles can be deflected from the outer magnetosphere and especially the magnetotail, directed along field lines into Earth's ionosphere, where atmospheric atoms can be excited and ionized, causing the aurora. 142. Orbit and rotation. Earth's rotation period relative to the Sun, its mean solar day, is 86,400 seconds of mean solar time, 86,400.0025 SI seconds, 143, because Earth's solar day is now slightly longer than it was during the 19th century due to tidal deceleration. Each day varies between 0 and 2 milliseconds longer than the mean solar day. 144, 145, Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference Systems Service, IERS, is 86,164.0989 seconds of mean solar time, UT1, or 23 hours 56 minutes 4.0989 seconds. 4. N10, Earth's rotation period relative to the precessing or moving mean March equinox, when the Sun is at 90 degrees on the equator, is 86,164.0905 seconds of mean solar time, UT1, 23 hours 56 minutes 4.0905 seconds. 4. Thus the sidereal day is shorter than the stellar day by about 8.4 ms, 146, apart from meteors within the atmosphere and low-orbiting satellites. The main apparent motion of celestial bodies in Earth's sky is to the west at a rate of 15 degrees. Earth orbits the Sun at an average distance of about 150 million kilometers, 93 million miles, every 365.2564 mean solar days, or one sidereal year. This gives an apparent movement of the Sun eastward with respect to the stars at a rate of about 1 degree. The Hill sphere, or the sphere of gravitational influence. of Earth is about 1.5 million kilometers, 930,000 miles, in radius, 151 n11. This is the maximum distance at which Earth's gravitational influence is stronger than the more distant Sun and planets. Objects must orbit Earth within this radius, or they can become unbound by the gravitational perturbation of the Sun. 151. Earth, along with the Solar System, is situated in the Milky Way and orbits about 28,000 light-years from its center. It is about 20 light-years above the galactic plane in the Orion Arm. 152. Main article. Axial tilt section. Earth's axial tilt, or obliquity, and its relation to the rotation axis and plane of orbit. The axial tilt of Earth is approximately 23.439281 degrees, 4, with the axis of its orbit plane always pointing towards the celestial poles. Due to Earth's axial tilt, the amount of sunlight reaching any given point on the surface varies over the course of the year. This causes the seasonal change in climate, with summer in the northern hemisphere occurring when the Tropic of Cancer is facing the Sun, and in the southern hemisphere when the Tropic of Capricorn faces the Sun. In each instance, winter occurs simultaneously in the opposite hemisphere. During the summer, the day lasts longer, and the Sun climbs higher in the sky. In winter, the climate becomes cooler and the days shorter. 153. Above the Arctic Circle and below the Antarctic Circle there is no daylight at all for part of the year, causing a polar night. And this night extends for several months at the poles themselves. These same latitudes also experience a midnight sun, where the Sun remains visible all day. 154, 155, by astronomical convention. The 4 seasons can be determined by the solstices, the points in the orbit of maximum axial tilt toward or away from the Sun, and the equinoxes, when Earth's rotational axis is aligned with its orbital axis. In the Northern Hemisphere, winter solstice currently occurs around the 21st of December. Summer solstice is near the 21st of June. Spring equinox is around the 20th of March and autumnal equinox is about 22 or the 23rd of September. In the Southern Hemisphere, the situation is reversed, with the summer and winter solstices exchanged and the spring and autumnal equinox dates swapped. The angle of Earth's axial tilt is relatively stable over long periods of time. Its axial tilt does undergo nutation, a slight irregular motion with a main period of 18.6 years, 157. The orientation, rather than the angle, of Earth's axis also changes over time, processing around in a complete circle over each 25,800-year cycle. This precession is the reason for the difference between a sidereal year and a tropical year. Both of these motions are caused by the varying attraction of the Sun and the Moon on Earth's equatorial bulge. The poles also migrate a few meters across Earth's surface. This polar motion has multiple, cyclical components, which collectively are termed quasi-periodic motion. In addition to an annual component to this motion, there is a 14-month cycle called the Chandler wobble. Earth's rotational velocity also varies in a phenomenon known as length of day variation. 158, in modern times. The Moon is a relatively large, terrestrial, planet-like natural satellite, with a diameter about 1/4 of Earth's. It is the largest moon in the Solar System relative to the size of its planet. Although Charon is larger relative to the dwarf planet Pluto, 161, 162, The natural satellites of other planets are also referred to as moons. After Earth's 163, the most widely accepted theory of the Moon's origin, the giant impact hypothesis, states that it formed from the collision of a Mars-sized protoplanet called Theia with the early Earth. This hypothesis explains, among other things, the Moon's relative lack of iron and volatile elements and the fact that its composition is nearly identical to that of Earth's crust. 41. The gravitational attraction between Earth and the Moon causes tides on Earth. 164. The same effect on the Moon has led to its tidal locking. Its rotation period is the same as the time it takes to orbit Earth. As a result, it always presents the same face to the planet, 165, as the Moon orbits Earth. Different parts of its face are illuminated by the Sun, leading to the lunar phases. 166. Due to their tidal interaction, the Moon recedes from Earth at the rate of approximately 38 mm. The Moon may have dramatically affected the development of life by moderating the planet's climate. Paleontological evidence and computer simulations show that Earth's axial tilt is stabilized by tidal interactions with the Moon. 169. Some theorists think that without this stabilization against the torques applied by the Sun and planets to Earth's equatorial bulge, the rotational axis might be chaotically unstable, exhibiting large changes over millions of years, as is the case for Mars, though this is disputed. 170. 171. Viewed from Earth. The Moon is just far enough away to have almost the same apparent sized disk as the Sun. The angular size, or solid angle, of these two bodies match because, although the Sun's diameter is about 400 times as large as the Moon's, it is also 400 times more distant. 148. This allows total and annular solar eclipses to occur on Earth. Earth's co-orbital asteroids population consists of quasi-satellites, objects with a horseshoe orbit and Trojans. There are at least 5 quasi-satellites, including 469,219 Kamoa-Alewa, 173, 174, a Trojan asteroid companion, 2010 Takas, is librating around the leading Lagrange triangular point, L4. In Earth's orbit around the Sun, 175, 176, the tiny near-Earth asteroid 2006 RH-120 makes close approaches to the Earth-Moon system roughly every 20 years. During these approaches, it can orbit Earth for brief periods of time. 177. As of April 2020, there are 2,666 operational, human-made satellites orbiting Earth. 8. There are also inoperative satellites, including Vanguard 1, the oldest satellite currently in orbit, and over 16,000 pieces of tracked space debris. N3, Earth's largest artificial satellite is the International Space Station. The abundance of water on Earth's surface is a unique feature that distinguishes the blue planet from other planets in the Solar System. Earth's hydrosphere consists chiefly of the oceans, but technically includes all water surfaces in the world, including inland seas, lakes, rivers, and underground waters down to a depth of 2,000 meters, 6,600 feet. The mass of the oceans is approximately 1.35 times 1018 metric tons, or about 1. The biosphere has significantly altered its atmosphere. Oxygenic photosynthesis evolved 2.7 GYA, forming the primarily nitrogen-oxygen atmosphere of today. 61. This change enabled the proliferation of aerobic organisms and, indirectly, the formation of the ozone layer due to the subsequent conversion of atmospheric O2 into O3. The ozone layer blocks ultraviolet solar radiation, permitting life on land. 193. Other atmospheric functions important to life include transporting water vapor, providing useful gases, causing small meteors to burn up before they strike the surface, and moderating temperature. 194. This last phenomenon is known as the greenhouse effect. Trace molecules within the atmosphere serve to capture thermal energy emitted from the ground, thereby raising the average temperature. Water vapor, carbon dioxide, methane, nitrous oxide, and ozone are the primary greenhouse gases in the atmosphere. Without this heat retention effect, the average surface temperature would be -18 degrees Celsius, 0 degrees Fahrenheit, in contrast to the current 15 degrees Celsius, 59 degrees Fahrenheit, 195, and life on Earth probably would not exist in its current form. Earth's atmosphere has no definite boundary, slowly becoming thinner and fading into outer space. 3/4 of the atmosphere's mass is contained within the first 11 kilometers, 6.8 miles, of the surface. This lowest layer is called the troposphere. Energy from the sun heats this layer, and the surface below, causing expansion of the air. This lower density air then rises and is replaced by cooler, higher density air. The result is atmospheric circulation that drives the weather and climate through redistribution of thermal energy. 197. Hurricane Felix seen from low Earth orbit. September 2007 – Massive clouds above the Mojave Desert. February 2016 – The primary atmospheric circulation bands consist of the trade winds in the equatorial region below 30 degrees latitude and the westerlies in the mid-latitudes between 30 degrees and 60 degrees. 198. Ocean currents are also important factors in determining climate, particularly the thermohaline circulation that distributes thermal energy from the equatorial oceans to the polar regions. 199. The amount of solar energy reaching Earth's surface decreases with increasing latitude. At higher latitudes, the sunlight reaches the surface at lower angles, and it must pass through thicker columns of the atmosphere. As a result, the mean annual air temperature at sea level decreases by about 0.4 degrees Celsius, 0.7 degrees Fahrenheit, per degree of latitude from the equator. 200. Earth's surface can be subdivided into specific latitudinal belts of approximately climate, ranging from the equator to the polar regions. These are the tropical, or equatorial, subtropical, temperate and polar climates. 201. Further factors that affect a location's climates are its proximity to oceans, the oceanic and atmospheric circulation, and topology. 202. Places close to oceans typically have colder summers and warmer winters, due to the fact that oceans can store large amounts of heat. The wind transports the cold or the heat of the ocean to the land. 203. Atmospheric circulation also plays an important role. San Francisco and Washington, D.C. are both coastal cities at about the same latitude. San Francisco's climate is significantly more moderate as the prevailing wind direction is from sea to land. 204. Finally, temperatures decrease with height, causing mountainous areas to be colder than low-lying areas. 205. Water vapor generated through surface evaporation is transported by circulatory patterns in the atmosphere. When atmospheric conditions permit an uplift of warm, humid air, this water condenses and falls to the surface as precipitation. 197. Most of the water is then transported to lower elevations by river systems and usually returned to the oceans or deposited into lakes. This water cycle is a vital mechanism for supporting life on land and is a primary factor in the erosion of surface features over geological periods. Precipitation patterns vary widely, ranging from several meters of water per year to less than a millimeter. Atmospheric circulation, topographic features, and temperature differences determine the average precipitation that falls in each region. Commonly used Köppen climate classification system has 5 broad groups: humid tropics, arid, humid middle latitudes, continental and cold polar, which are further divided into more specific subtypes. 198. The Köppen system rates regions based on observed temperature and precipitation. 207. Surface air temperature can rise to around 55 degrees Celsius. 131. Degree F, in hot deserts, such as Death Valley, and can fall as low as -89 degrees Celsius, -128 degrees Fahrenheit, in Antarctica. Above the troposphere, the atmosphere is usually divided into the stratosphere, mesosphere, and thermosphere. 194. Each layer has a different lapse rate, defining the rate of change in temperature with height. Beyond these, the exosphere thins out into the magnetosphere, where the geomagnetic fields interact with the solar wind. 210. Within the stratosphere is the ozone layer, a component that partially shields the surface from ultraviolet light and thus is important for life on Earth. The Kármán line, defined as 100 kilometers, 62 miles, above Earth's surface, is a working definition for the boundary between the atmosphere and outer space. 211. Thermal energy causes some of the molecules at the outer edge of the atmosphere to increase their velocity to the point where they can escape from Earth's gravity. This causes a slow but steady loss of the atmosphere into space. Because unfixed hydrogen has a low molecular mass, it can achieve escape velocity more readily, and it leaks into outer space at a greater rate than other gases. 212. The leakage of hydrogen into space contributes to the shifting of Earth's atmosphere and surface from an initially reducing state to its current oxidizing one. Photosynthesis provided a source of free oxygen, but the loss of reducing agents such as hydrogen is thought to have been a necessary precondition for the widespread accumulation of oxygen in the atmosphere. 213. Hence the ability of hydrogen to escape from the atmosphere may have influenced the nature of life that developed on Earth. 214. In the current oxygen-rich atmosphere, most hydrogen is converted into water before it has an opportunity to escape. Instead, most of the hydrogen loss comes from the destruction of methane in the upper atmosphere. 215. Life on Earth. Extreme weather, such as tropical cyclones, including hurricanes and typhoons, occurs over most of Earth's surface and has a large impact on life in those areas. From 1980 to 2000, these events caused an average of 11,800 human deaths per year. 225. Many places are subject to earthquakes, landslides, tsunamis, volcanic eruptions, tornadoes, blizzards, floods, droughts, wildfires, and other calamities and disasters. 226. Human impact is felt in many areas due to pollution of the air and water, acid rain, loss of vegetation, overgrazing, deforestation, desertification, loss of wildlife, species extinction, soil degradation, soil depletion and erosion. 227. There is a scientific consensus that humans are causing global warming by releasing greenhouse gases into the atmosphere. 228. This is driving changes such as the melting of glaciers and ice sheets, a global rise in average sea levels, and significant shifts in weather. 229. H. The first human to orbit Earth was Yuri Gagarin on 12 April 1961. 240. In total, about 550 people have visited outer space and reached orbit as of November 2018, and, of these, 12 have walked on the Moon. 241. 242. Normally, the only humans in space are those on the International Space Station. The station's crew, made up of 6 people, is usually replaced every 6 months. 243. The farthest that humans have traveled from Earth is 400,171 kilometers, 248,655 miles, achieved during the Apollo 13 mission in 1970. 244. N. Human cultures have developed many views of the planet. 255. The standard astronomical symbol of Earth consists of a cross circumscribed by a circle. 256. Representing the 4 corners of the world. Earth is sometimes personified as a deity. In many cultures it is a mother goddess that is also the primary fertility deity. 257. Creation myths in many religions involve the creation of Earth by a supernatural deity or deities. 257. The Gaia hypothesis, developed in the mid-20th century, compared Earth's environments and life as a single self-regulating organism, leading to broad stabilization of the conditions of habitability. 258, 259, 260 images of Earth taken from space, particularly during the Apollo program, have been credited with altering the way that people viewed the planet that they lived on, emphasizing its beauty, uniqueness and apparent fragility. 261, 262. Scientific investigation has resulted in several culturally transformative shifts in people's view of the planet. Initial belief in a flat Earth was gradually displaced in ancient Greece by the idea of a spherical Earth, which was attributed to both the philosophers Pythagoras and Parmenides. 263, 264. Earth was generally believed to be the center of the universe until the 16th century, when scientists first concluded that it was a moving object, comparable to the other planets in the Solar System. 265. It was only during the 19th century that geologists realized Earth's age was at least many millions of years. 266. Lord Kelvin used thermodynamics to estimate the age of Earth to be between 20 million and 400 million years in 1864, sparking a vigorous debate on the subject. It was only when radioactivity and radioactive dating were discovered in the late 19th and early 20th centuries that a reliable mechanism for determining Earth's age was established, proving the planet to be billions of years old.